glad to introduce you Sarah Hülsen. She is a PhD student with the Weather and Climate Risk Group at ETH Zurich, Switzerland. Her work focuses on extreme weather impacts on ecosystems and implications for ecosystem services. To this end, she used various methods, including probabilistic risk modeling and remote sensing. Sarah is also a developer for the Climata open source climate and weather risk modeling platform. So thank you so much for that invitation, and the floor is yours.
Thank you. Yeah, thanks for the introduction. Yeah, thank you, Sibeli, for the introduction. Thank you for having me here. I'm really excited to share some of my research with you and then also hear what your associations are with it and maybe, yeah, just some reactions from your side. So as Sibeli mentioned, my name is Sarah Hülsen. I'm based at ETH Zurich in Switzerland. And the agenda for today, I'm going to go a little bit over the background of my research and more generally my group's research and how we're thinking about these climate risk issues and the methodologies that we use to approach them. And I'll talk a little bit about ecosystems for disaster risk reduction, so ecosystem as a tool. And then the other side of the coin, disaster risk affecting ecosystems. And I'll talk a little bit about a recent publication that we've authored with collaboration with Laura D. From the University of Colorado Boulder, who some of you might know, who's my co-advisor for the PhD. And then I'll talk a little bit about the outlook and some future work that we're planning. So on the background, the Weather and Climate Risk Group, we focus mostly on societal resilience to extreme weather and climate change. And we are aiming to provide policymakers with the necessary information that is needed to assess risk and then also mitigation and adaptation options for those risks and tools to design adaptation strategies. So to that end, we're trying to establish a certain risk management approach and a risk modeling approach that helps us to really put a number on local climate risk, but also do this in a globally consistent way so that we can also compare different areas to one another, which also facilitates learning from different areas. And we're working a lot with projections of climate change and extreme weather patterns, and also scenarios based on some of the work that's also being done by the IPCC and the impact modeling community at large. So a lot of you might have seen an iteration of this. This is basically just a visualization of the IPCC's definition of risk, which is defined as the convolution of hazard, exposure, and vulnerability. Hazard being the natural or partly human-driven phenomenon that might impact an area. So that could be storms, floods, fires. I think all of us, unfortunately, are familiar with several examples. The exposure is then the value that we're interested in, the value at risk. And traditionally, this has often been physical assets, but one of the aims in our group is to make this more people-centric and also account for a lot of the losses and damages that aren't really capable to just put an economic number on. So this might also be people, access to basic services, or in my case, ecosystems. And the vulnerability then describes the susceptibility of the exposure to be impacted by the hazard. Yeah, so I already mentioned a few examples of this. Some of the hazards that we're studying in our group are tropical cyclones. So in North America, you would refer to those as hurricanes, floods, and Europe, windstorms, especially winter storms, are really important as well. But there's really any type of hazard data that you could look at in this case. And then some examples for exposures could be economic exposures, people, crops, ecosystems, you name it. And we have implemented this in the Climata modeling platform, which basically just allows different users to combine these three different types of data in an efficient way and to map impacts spatially explicitly. This can also then be used to investigate the impact of different climate scenarios. So maybe compare low emission pathways with high emission pathways and see how that changes the risk. but also with different development scenarios. So for example, economic development and population development also play a really big role in how risk develops in the future. And then of course, you can also look at how different adaptation options might influence resilience. Ecosystems in nature traditionally feature in this framework mostly as tools for disaster risk reduction. So they kind of come in through the resilience measures arrow here. And this is often under the umbrella of nature-based solutions or ecosystem-based adaptation. There's a bunch of different terminologies and research areas in this area. So this brings me to the ecosystems for disaster risk reduction part. And this is really how I first started studying this. So I think a lot of us know some examples of how ecosystems could be used for the disaster risk reduction. So green infrastructure, for example, is really key in reducing urban heat island effects and can reduce the impact of heat waves. But coastal ecosystems are also a really popular example for reducing the impact of storms and storm surges. So this is what my first publication has dealt with, which was called Global Protection from Tropical Cyclones by Coastal Ecosystems, Past, Present, and Under Climate Change. And this was a work done in collaboration with the Nature Conservancy and some other colleagues, both in the US and the UK. And here we used the INVEST Coastal Vulnerability Model. INVEST is an ecosystem service modeling platform, mostly under the Natural Capital umbrella. And they have some data which links coastal habitats to a protective potential that they might have in case of storms. So this is both for individual coastal habitats and also combinations of those. So for example, mangroves by themselves have a fairly high protective potential, but combined with seagrass meadows or coral reefs, this potential can be even higher, and this is what is reflected in that data. We then coupled that INVEST data with the Climada risk modeling by linking population in low elevation coastal zone to the ecosystem that they might receive the protective benefit from. And through that, we were able to generate a spatial overlay of the populations at risk and the ecosystems that could provide potential benefits. And that also allowed us to model the annual number of people that are impacted by tropical cyclones and also the annual number of people that receive these protective benefits. So with the temporal view on this, over the last 30 years, there has been a decrease in the population that is receiving these protective benefits. And this is mainly due to ecosystem loss and degradation, which leads to currently only 1 in 5 people impacted by tropical cyclones being within the protective distance of these ecosystems. We then also looked at how changes in tropical cyclone activity might impact people in the future. And unsurprisingly, in the future, we expect the number of people to be impacted to increase. But unfortunately, this occurs predominantly in areas that are currently unprotected by coastal ecosystems. So here, this is really about what I was mentioning earlier, the perspective of how the role of ecosystems has changed and might change for protecting people. But this also raised some other questions to me. So for example, okay, now we know that ecosystems are important for people, for adaptation, for disaster risk reduction, but how does extreme weather actually impact the ecosystem themselves? And how does this change with climate change? And then also in turn, how do these impacts propagate back to the people that are dependent on the ecosystem? So what does this mean for these adaptation options and how effective they will be in the future? So this then brings me to the next part of the talk, which is the disaster risk for the ecosystem. So how ecosystems themselves are affected by extreme weather. And here we had to do some conceptual work before we were able to kind of jump right into the modeling, because the basic recognition from ecology is that ecosystems are adapted to, and in some cases even dependent on, the disturbances that they are historically experiencing, so the historical disturbance regime. And that means that the damage concept that we use in impact modeling can't just directly be translated to ecosystem, because if we see that a house is destroyed by a storm, we can probably say, okay, this is just a net negative. And then maybe depending on how people cope with recovery, there can be some positive aspects to this, but the initial impact is pretty much just a negative one. However, with ecosystems, that's not necessarily the case because they have co-evolved with these natural hazards. So in the case with, for example, cyclones, a category 5 tropical cyclone isn't necessarily always bad. So then how can we represent this in our modeling? And here we arrived at the thought that the relevant measure is actually the departure from historical conditions. So it's about these novel disturbance regimes, which is a concept that was recently coined by Turner and Seidel in a really great publication that I can recommend to everyone. So the idea here is that you have a variety of different disturbance characteristics, and some refer to the regime that the ecosystem experiences, and then others refer to the response in the system. And if multiple of those depart further and further from their historical range of variability, that increases the risk of reorganization in the ecosystem, changes in ecosystem function and structure, and at the most extreme end of the spectrum, that could lead to a regime shift. So then, coming from a climate and hazard modeling perspective, I thought that there's especially two characteristics of disturbance regimes that we are kind of uniquely positioned to tackle, mainly the return interval, or you could also call it frequency and intensity of hazards. And this is because we have climate models and hazard models that allow us to overcome certain limits of the historical record. So in a lot of cases, we only have, 10 to maybe 50 years of really good, reliable data on a lot of physical hazards. And of course, this is not really a good representation of the actual risk experienced anywhere in the world. But with a combination of dynamical and statistical models, you can fill in these gaps and also assess tail risk and these kind of low probability, high impact events. So that allows us to then establish a reliable baseline and also to investigate these departures in terms of historical hazard intensities and frequencies. And this was really what my most recent publication was about, which Laura D. Co-authored, and then also some other people from my group here and some colleagues at Stanford, which was about mangrove ecosystems and their services and how they might be at risk from tropical cyclones and sea level rise under climate change. So these were the methods that we employed here. If you focus first on the left side of the flowchart, this is the tropical cyclone part of the methodology, where basically we used downscaled CMIP6 climate models to obtain tropical cyclone tracks for different socioeconomic shared pathways. So this is different climate scenarios by the end of the century. And then from this, we calculated the wind fields and frequencies at each grid point that is affected by tropical cyclones globally, which then allowed us to calculate the relative change and frequency at each mangrove location. On the right side of the flowchart, this is the sea level rise data. So there we used, again, CMIP6 projections for the same emission pathways and calculated from that the median rate of sea level rise at all mangrove locations, and combined this with some adaptive capacity thresholds known from previous research, which basically looked at to what extent mangroves will be able to adapt to sea level rise and at what point adaptive capacity limits might be reached. We then merged the tropical cyclone and sea level rise data with global mangrove locations, which gave us a composite risk index. And this, in turn, we combined with information on mangrove biodiversity the sea level rise data, we then have 3 different versions. So from left to right, this would be increasing emission pathways. And the different colored points represent the median rate of sea level rise at all mangrove locations. And the lighter the points, the higher the sea level rise that is expected, or the rate of sea level rise that is expected. And here you can already see that with higher emissions, more and more of the areas fall into this category where it becomes really unlikely for mangroves to be able to adapt. We then did something similar with the tropical cyclone data. Here it's important to note that these wind speeds refer to really the wind speed at the location. So this is the actual hazard intensity experienced by the ecosystem, not an overall storm category. And TC1, 2, and 3 are kind of the categories that we defined here ourselves, but they would correspond to category 1 and 2 on the Saffir-Simpson hurricane scale for TC1. TC2 would then be category 3 and 4 winds, and TC3 would be category 5. So these are the really, really high intensity winds that are super rare, even if you have an overall storm that's category 5. Of course, you will not have category 5 winds at every location. So this is really the highest that it gets. And here we can also see that with increasing emissions, the areas that will fall into this highest category become more and more widespread. And I should mention substantial change in frequency we defined as either a doubling in frequency for the given intensity category, or an area being completely newly affected by that category. We then combined the sea level rise and TC data in this risk index, as I mentioned before. And basically the matrix you can see on the top right just shows how the different TC category and sea level rise category result in the final risk rank. And we did it in this way to reflect that increasing sea level rise also increases the vulnerability of mangroves to tropical cyclones and vice versa. So it's really this compounding impact that occurs there. So looking at some numbers, you don't need to look at all of them in the table. The main thing you need to know is there's, again, the different emission pathways. So 245 being the lowest emission pathway, and then 585 being the highest. And then the top row in each of these refers to the total global mangrove extents, and the top 25% and top 10% refers to a ranking of mangrove areas in terms of the highest levels of biodiversity and ecosystem service provision. And there's 2 key takeaways here, which is that approximately half of global mangrove extents are at high to severe risk, regardless of the emission scenario. So for SSP 585, it's a bit more, but even at the lowest emission scenario, we already have quite a substantial area at risk. And then another unfortunate finding that we had here was that the highest ranking areas in terms of ecosystem service provision and biodiversity are at disproportionately high risk. So you can see, for example, in SSP 585, in the severe category, there's about 20% of all global mangroves that are in this severe risk category. But for the top 10% ranking in terms of ecosystem service, this is almost 35%. So then zooming into the different locations where people might be dependent on these services, we can see that unfortunately, whether we look at Central America, Southeast Africa, Southeast Asia, or the Southwest Pacific, in all of these, we have areas that are at really high levels of risk. But there is some regional patterns here, and also the ecosystem service provision is not necessarily at the same levels of risk globally. So the numbers, the letters here refer to P being protection for people, A, protection for economic assets, F, fishing benefits, and then C, carbon. And we can see that especially in Southeast Asia, there's very high shares of these ecosystem services at risk. And another takeaway here is that in all cases, the E, so the areal extent of the mangrove, doesn't necessarily correspond with the share of ecosystem services at risk. So another takeaway that we had from this was that just mapping an ecosystem area at risk is not necessarily a good indicator of the ecosystem services at risk, and that this explicit mapping for the services is necessary. Another finding that I wanted to highlight from this paper, and you can't really see the title, but it should say, okay, I can't really move the mouse there. Yeah, here we go. Sorry about that. Yeah, so we also projected where areas might experience non-analog disturbances under climate change. So that would mean that what we've modeled before, in some areas, there's locally a very high change in the conditions that will be experienced, but it might be similar to the current conditions that are experienced elsewhere. So, for example, the Philippines is an area that today has the highest level of tropical cyclone activity. So in the future, in other basins, they might become more similar to what is already experienced there. But unfortunately, we found that in Southeast Asia and especially the Philippines, these areas will experience tropical cyclones at frequencies that are currently unprecedented. So this figure basically shows, again, for the different intensity categories, which are the rows, and the different SSPs, which are the columns. It highlights points that will in the future experience frequencies that are not currently experienced elsewhere. And we can see that, for example, for the 70 meter per second, which is the category 5 wind speeds, there will be some areas in the Philippines that will experience almost a tripling or even more in frequency. So this then raises a lot of uncertainty about the ecological consequences of these natural hazards in the future and how the ecosystem might respond to these disturbances. Find my mouse again. Oh. Yeah, here we go. It's a little breather for everyone. I think that's good. So what we did here, basically, if you look at, again, this is a figure from Turner and Seidel, where they mapped this novelty and disturbance regimes and the probability of regime shifts as a function of both the regime that changes, so in our case, the natural hazard that changes, and then also the response that changes. We mainly covered the x-axis of this. So we looked at how are tropical cyclones changing and where is this occurring in relation to the mangrove ecosystem. Moving forward, we want to include the other axis of this more explicitly. So look at what does this mean for ecological responses? What does this mean for the ecosystem? And again, what's the spatial relationship between these ecological changes and the changes and the hazard? And with this, I'm really excited to be working with Sibeli and to tap into some of her remote sensing expertise and hopefully be able to, again, couple some of the methods that are being used more on the ecological and remote sensing side of things with the hazard data and the modeling that we are doing on our end of the spectrum. So with that, thank you for your attention. I'm happy to take any questions.